Yeah, thank you so much for the introduction, and thank you so much for having me here. Hi everyone, I'm Nishant Garg. I'm an assistant professor at University of Illinois, and I'm going to talk about how we can use CSH seeds, another nanomaterial, for enhancing strength and reducing porosity in concrete. I should say here that I gave a very similar talk yesterday, so those of you who attended that, it is going to be more or less the same content. So I just want to say that beforehand, it's just how this work done by one of my PhD students fits in two different topics. Yeah, that being said, if you're here, that's all right. Okay, all right. So to get started here, and I know there's a lot of students at ACI, and I think the one thing ACI really does well, other than all other organizations, is makes the student participation free. Right? The registration is free. And I know the best way to communicate with students is through memes. So I'm going to start off with a meme here. And this is one that I like. And if you think about it in the context of low carbon concrete, you can have this kind of situation where the one spouse is thinking, right, I bet he's thinking about other women, but the guy is like, what can I do about the early strength of my low carbon concrete, right? And I should be very clear here that the low carbon concrete, when I talk about it, I'm really talking about the high SCM concrete, right? When you have 40, 50, 60% dilution of clinker with SCMs, the early strength really starts to suffer, right? So this is not talking about other chemistries like CSA, or if you make potent cement from other ways, it's really high SCM concrete. So if somebody can solve this, I think there's a lot of potential there. Other than early strength, I think workability also tends to suffer, so you could also insert that depending on what kind of pozzolan are you using. If it's a high water absorbing pozzolan, that's another one. All right, so let's get started with the technical things here. So we know that when we talk about different scales, we can have macro, micro, and nano, and macro is what gets used and placed in the real world, right? And then micro is, if we consider the cement ingredient of concrete, it's really it's kind of a micron-sized material, and it's a mixture of, I like to call it, many different spices, right? It's a single-looking spice, but it's a mixture of many different spices, all micron-sized. And then you can also go to the nanoscale. I don't have a picture for a nanoscale because you can't really see the nanoscale material, but I do promise you later on I do have some TEM images of some of these CSH seeds that we collected recently. And our group has done a lot of work on the macro size, so I'm going to spend a few slides talking about it. And there's a technique that we've been working on for almost now 5 years, which is Raman imaging. And how it works is essentially if you start off with this is an optical image of a aggregate of a granite rock specimen. And what you do is that you basically take these point by point grid-like fashion spectra at different points in this map. And then you get a representative spectra at every location. This spectra you can then categorize and assign to different phases that are present, right, to get direct mineral information. So kind of very similar to, you can say, SCM EDS, but instead of getting elements, you get mineral phases directly. Okay. And then you can have a spatial distribution. So the colors represent the different phases that are present. So in this case, you have quartz, feldspars, and so on that are in this aggregate. And this is actually routinely done in many other industries. So here's an example, and I'm just going to blow it up here. And since I'm in the middle of a semester, right after this talk, I have to go and teach a class. So I'm going to be in the kind of asking you some questions here. Can anybody guess what this material is? And I can bet many of you have put this material in your mouth at some point in your life. Excedrin, right? So this is an over-the-counter decongestant, over-the-counter painkiller, or Excedrin, and you can see clearly you have aspirin, you have acetaminophen, which is Tylenol, and then you have caffeine, right? So the pharmaceutical industry already uses techniques like this to not only quantify the ingredients that they have in a system, in a pill, this is a cross-section of a pill, so that they have quality control, but also to see the spatial distribution, right? So again, if they had bad quality control, and if all the caffeine was on one side of the pill, and if you're somebody like me who just breaks the pill in half and only take half of it, I'll just get high on caffeine and not get the Tylenol, right? Which you need when you're sick. So what we thought, well, why don't we do the same thing on cement, right? And people have been doing that with SCM EDS for a long time. We want to do this with Raman imaging and see what we can get. So we make this kind of a little pill, which is essentially cement embedded in epoxy. We get this very high resolution Raman image. We can quantify most of the phases. Each of this image that you're looking at has 250,000 pixels in it. So it's a really high resolution image at a large area, 5 millimeters by 5 millimeters, which gives us statistics that it can then correlate with the bulk XRD measurements. We did this on a variety of 11 different cements from the US. We get a decent correlation. And we can then start to obtain these very interesting phase-specific maps, right? So if you look at this here, you have now the A-light map. So this is zoomed in version on the right here. You can start to see the individual A-light grains in the system, right? So it's kind of looking at a Google map, and you're zooming in to that specific location. And then you can obtain all these different maps for all individual phases, even down to something like quartz, which is at the order of 1%, and you can quantify it, okay? All right, another quiz, and you may get extra credit for this. Can anybody guess what phase is this? So again, this is a bit tricky one. So this is actually not a Raman image. This is actually an iPhone photo of the night sky that my student took. Right? And you can see that this is kind of very similar to what we're doing is similar to what astronomers do. In this picture, the white pixels are the stars, but what we have in the Raman image are the stars of the clinker, right? The clinker phases. So what else can we get out of this? Well, you can actually get the size and the shape distribution now of individual clinker phases, right? Again, this is just a short animation of going through the different phases that are distributed in this image. And then you can quantify this through image analysis, and you can get what we call the phase-specific particle size distributions, right? So instead of having a global PSD, you can get the PSD for each component within the cement. So all the way from A-light down to calcite or quartz. And the interesting thing for me now, the next thing I'm thinking about is, we hear a lot about type 1L cements and the variability and so on. It is possible, right, hypothetically, you could have two type 1L cements with the same amount of limestone, 10% limestone, but depending on the grinding done at the different plants, the fineness of the limestone in one cement could be different from the other, and different depending on the PSD curve, you could have different water demand and different strength. So that's something would be very exciting to figure out. So if you want to kind of collaborate on that, just let me know. I'm looking to get more kind of cement samples. Then you can get all sorts of other things. You can look at the shape. You can generally see that B-light has a lower aspect ratio than A-light, and we know that B-light is generally rounder because it's softer, so it gets ground up like that, and we can now quantify that. This work came out last year in JPCC. It made it on the cover, so we are kind of really looking forward to take it from here. How can we kind of better understand this? I was trying to explain this to my kids, and I thought M&Ms would be a good way to explain them. If you think about the cement is a box of M&Ms, you can think of all the cement phases as these different colored M&Ms. And here, you can think of them, all of them being equal size and equally distributed, but in reality, they're kind of random, different sizes, different shapes, and different way they're oriented. So what we can then do is we can build what we have as a very empirical equation here we call the CSQ, which takes into account not only the bulk composition, but the individual particle size distributions of these curves, and we can get a reasonably decent agreement with the 3-day cumulative heat for a series of 10 cements. Right? So you can imagine this, at some point in the future, we can feed these large images into some kind of advanced machine learning model, and you can start to predict the hydration a little bit better than what you would do with just with the phase composition. Okay, I come back to the nano, and I know the session is about the nano, so I want to spend some time there, but I think there's a lot of room of optimization at the micro scale. If you consider the nano, one of the things we've been looking at was CSH seeds, and I thought, it's kind of interesting to see always what's happening in the literature, and you can see that there's about maybe 60 papers that have been published very recently on an annual basis. Some of the early papers in 2009 by Jeff Thomas and Ali Zadeh were kind of the beginning papers, and then it's not just fair to look at the papers with a particular term. You should also look at what's happening to the field. Any idea how many papers we are publishing with the word cement in them? Just give me a number. 10,000? 10,000 is actually close. Anybody else? We can play Price is Right.
2001.
Oh, okay. Sorry? 10,001? Oh, I think you saw my presentation yesterday. So 30,000 is the correct answer. ladies and gentlemen. So, but then what you should do is, whatever term you're looking for, you should normalize it by the overall field. Let's say in this case, cement. Maybe I should have done with concrete. Anyway, if you do that, the normalized data says currently the 0.2% is kind of the trend. So it is increasing. That means there is a little bit more interest. And somehow this also matches with the dosage that these guys recommend. So that's kind of a fun thing. Anyway, anybody know what happened around here? Or what I hypothesize things started to take off? So one of the things was one of the patents related to these seeds by Luke Nicolau was kind of, came out here. There was this early papers also in 2009, as I said, which talk about seeding. So they are not listed here because they don't have the CSH seed in their title, but the seeding papers also came out in 2009, and this patent, and then things kind of take off from there. All right, I think that's all I want to say on this. So in terms of research objectives, what we wanted to do here is look at a very commercial, off-the-shelf product, right? This was specifically for, and you can read off these research objectives. We work with the Illinois Department of Transportation. Their main goal was to open the pavement to traffic a little bit early, and we thought like one way to do that would be to kind of accelerate or enhance the strength using off-the-shelf commercial products. So we did not, I'm not going to talk about any synthetic versions or the ones you can make in the lab. In the lab, you can make a really huge variety and you can really tweak the properties. But the goal here was to use what a DOT can buy and use. And there also, I learned there's some restrictions on what is approved and not, so we did some tweaking based on that. And then we wanted to answer all these questions. Okay. And then we have a very standard lab testing protocol, and you'll see all sorts of kind of standard tests, which again were kind of prescribed by the DOT, which we did, and I'm going to show here, and I'm going to show a little bit of field implementation as well. If you look at the kinetics from the ISOCAL, again, very standard results. This has been reported in literature several times, right? Depending on the dosage, there's almost a direct correlation between the dosage and the acceleration that takes place. The cumulative heat also increases on the order of 15 to 20%, which means the overall hydration is enhanced. If you look at the two admixtures here, you have the Exceed 44 and you have the Exceed 55. And the interesting thing is these two admixtures actually behave slightly differently. One of them accelerates and one of them slightly retards the reaction, and which is kind of interesting, right? And what we understand is the reason is because of the amount of PCE and HRWR you have in them. But if you look at the overall heat, the cumulative heat is improved for both of them, so that is good because that's what ultimately for strength enhancement point of view, that's what matters. If you look at the compressive strength, again, generally we see an increase with depending on the dosage. If you look at the other thing I wanted to look at is the porosity, right? So there's a lot of strength data in the literature, but not much data on the porosity and the durability. So there we find that also the porosity goes down by a few percent as measured by helium picnometry. And after about like a dosage of 1 to 1.5%, this everything kind of plateaus. So the gains in porosity become marginal at some point, even though the kind of strength, there is an increase. So that's something to consider. And then if we look at some of the blended systems where you have OPC and as well as the fly ash, again, we see this reduction in porosity, which was good. And again, all of this data is available in this report that came out last year along with the papers. Then the other thing we have been exploring is a let's say, another technique to look at microstructure refinement, right? So this is laser profilometry. And some of these newer profilometers are pretty good. The resolution you can get on these systems is on the order of nanometers. And you can get a very detailed 3D map that you can build of the surface. And what we have found is that the surface maps, if it's large enough, done properly, can actually correlate to the porosity of a system. And what we have found, and there is a paper I'm going to mention here at the bottom, we've spent a lot of time, so this NPJ materials degradation paper last year, we find some really interesting correlations between the profilometry data and the surface roughness and the porosity of a system. So I think this technique could have a lot of potential to explore. At this point, we just correlate two of the parameters. One is the peak curvature, and the other is the peak density. And we find that it actually correlates with the open porosity from the helium picnometry. And I do a lot of characterization, and every time I find a correlation between two totally different techniques, it's like two people from two different places agreeing with each other, then I think something is happening, right? So I think that there's a lot of room here we should explore. Okay. So again, a bunch of other correlations. These are correlations between techniques which people have already explored. So whether it's the mass loss from TGA, or the formation factor, porosity versus strength, as well as the formation factor versus strength. Again, these are standard correlations one would expect. And again, we had to do this. This is also out last year. The other thing the DOT was really interested to explore was to say, okay, we want to compare formation factor versus compressive strength. And there were some interesting things we learned about that if you look at the lab data, you get almost a linear correlation between the two. But if you look at the field data, it's kind of a little bit all over the place. And I think again, our hypothesis here is the reason is because you have a cocktail of admixtures in the field, and there's the curing condition and so on. There's a lot of variation there. But generally, if you look at individual mixes, it does have a specific trend. Finally, we were able to implement this at a box culvert. Again, the DOT wanted to try it, and we were able to go through that process. And this was built. So this is kind of very kind of rewarding to see like a field application from what you work in the lab. And again, I think for them the most interesting part here, point out this part of the curve here, you see this kind of a bump in that early strength, right? And this allows them, if they want to open the pavement or the bridge deck early, or whatever they want to open early, right? I think again, to be very fair here, the strength gain is on the order of 15 to 20%, right? So from it's not going to be 50% or 80%, at least from these kind of commercial systems. If you make in the lab, you can definitely kind of make it kind of super doped. But on the commercial system, this is the order of strength that we're talking about. So people are also thinking of, you can then reduce your cement content by 10% or so, and then get that equivalent performance and get a different GWP and so on. If we look at some of how these seeds look under the TEM, and again, you kind of see these almost 50 to 100 nanometer sized particles, which are kind of uniformly distributed in this in the PCE network, and I think this is what kind of does the job. And if you look at the CSH individual particles, the images match pretty well what has been reported in the literature for synthetic CSH. If you do an X-ray diffraction on the dried version, you also get a typical CSH peaks. So from that point of view, the purity and the dispersion is done nicely in this product. Okay, so if I were to just kind of conclude here in terms of our contributions, right, the seeds can affect the kinetics depending on the dispersion medium. So you have to be careful in some of the systems. If you have a lot of PCE, you can have some retardation. But of course, you also need that from a workability point of view. So right, the strength and the kinetics and the workability is a trade-off. Based on helium picnometry and razor profilometry, there is evidence that we have this microstructure refinement, which is good from a durability point of view. So we kind of refine this picture of you have increased hydration, but also the microstructure is refined. Finally, this is now implemented in the field and is fully documented as part of a report. And with that, I want to thank my team, and specifically my PhD student Faisal, who led this work, and also the funding agency IDOT, and we work with ICT. And with that, I'm happy to take any questions.